Welcome back to biology class. My name is Mr. Kubuske. This is your biology class. Today we're going to be talking about the beginnings of Unit 9. Unit 9 actually is my favorite unit to talk about. It's all about evolution and how things change over time. But the reason I get so excited about it is because it's a chance to investigate some topics that students usually, by the time they have gotten to me, really don't understand or haven't gotten a chance to explore. Not only that, it gives us a chance to really use our critical thinking skills and build on ideas, take information, process it, and come up with our own answers. That's the great thing about evolution is there's not really one answer. Whatever you think, whatever your belief is, and whatever you can prove or disprove, that becomes truth to you, and that's important to me. That you take, all the different aspects, theories, all the different data, and kind of mash that into your own belief system. So today I'm going to present you with scientific information about the history of our universe. Okay, it's not theologic. I know this is a Catholic high school, and I'm very lucky in that I don't get a lot of pushback on the things that I teach as long as it has scientific backing. Plus the state of Indiana says, hey, you got to know some of this stuff. So that being said, keep in mind, I want you to formulate your own opinions, your own theories, your own beliefs. And I'm just presenting you scientific data. I'm not going to give you any of my own beliefs. I'm not going to give you any of my own personal theories. Okay? This is all scientific backed. Okay? That being said, let's talk about the beginning. In the beginning, all the matter in the universe condensed into one ball, and it got smaller and smaller and smaller until it became the size of an atom. And when that happened, we have something that's called the Big Bang. Now, what does that mean? Does that mean there was a giant explosion? Well, probably not an explosion per se, but what has happened is that from that tiny little atom, that teeny tiny little atom, that it contained, again, all the mass in the universe. So every planet, every person, every galaxy, every star was contained in that one little atom. From that point, things have now begun to expand, and they're moving to all different directions. Now, you may say, oh, so they're expanding to the edge of the universe. Well, the edge of the universe is actually what that thing that's expanding is. What is it expanding into? Well, it's expanding into nothingness. So as far as the stuff that we consider our universe is expanding into, that is the size of our universe. Now, how do we know our universe is expanding? Well, luckily, we live in an age where we have really powerful telescopes that we are able to actually see galaxies that are far, far away, and we can tell that they're actually moving apart from one another, or maybe they're moving away from us. And that tells us that obviously things have been given some type of momentum, and that the reason that they're moving in all these different directions is because of something known as the Big Bang. Okay, so a cataclysmic event that's caused debris to move in every different direction. Okay, so that is the Big Bang theory. It occurred roughly about 13.75, or if you want to round up, 13.8 billion years ago. Now you may say, how do we know that? Well, we've sent satellites and different machines out into space that actually collect some of what we call space dust, some space debris. Little tiny pieces, fragments left over from this Big Bang theory and from the collision of planets and formation of solar systems. And when we radioactive date them, when we do radioactive dating, we can actually tell the age of these rocks. And the majority of the rocks that we found, the oldest ones, they all go back to a point about 13.75 billion years ago. So that's how we can estimate the age of our universe. Okay. Within the first second of our universe's existence, within the first second after the Big Bang, every element on the periodic table was formed. Now, this happened because of something called quarks, which are smaller than the subatomic particles that we know as protons, neutrons, and electrons. The way that they conglomerated, the way that they bound together in this very exciting 1 second, you would be amazed all the things that happened in this 1 second. If you're really into quantum physics and stuff like that, I would highly suggest doing some more research in it because it is absolutely amazing. But anyway, so in that first second of the universe's existence, all the different elements of our universe were created. So all 118 that are on our periodic table were created in that moment. This obviously has caused the universe to expand, which we know it is still doing today. There are some that believe that it expands and contracts continuously. Like it'll go out to a certain point, and then when we get back to that point, it'll start contracting again, condense back down, and do another Big Bang. So in theory, this may not be the first time the Big Bang has occurred. Maybe it's occurred twice, or 7 times, or thousands of times. And each time creating a brand new universe with its own planets, its own galaxies, its own life forms. It's really kind of crazy when you really start to think about it. Okay? And more importantly, what happened during this period of the Big Bang, it sent debris and gas clouds and all kinds of stuff like moving in different directions. And those things would start to kind of conglomerate together. Certain gases that are created, again, in that first second will kind of conglomerate together, and some of these little debris particles that smash together, and that's going to kind of be the basis of what we know as planetary bodies, solar systems, and stars. Okay. All right. So how did our solar system form? Well, these gas clouds became so large that they actually started to condense on themselves. And you may say, well, how does that happen? Well, luckily, okay, I'm going to go to YouTube here. If I can click a couple of buttons. Sorry, I'm going to turn this off. If I click this button. Oh, I got no volume.
These two lead balls in this carousel. Now I'll step up here on top of the carousel. I've now increased my mass by the mass of two lead balls, and I'm holding them straight out. So now the mass in my body is distributed at a distance far from the center.
Fleming is impersonating a molecular cloud. The weights represent its mass, which to start with is spread over a huge area.
Now I'm going to ask Lucy to give me a hand here and give me a little bit of angular momentum. As I start spinning, I'm going to move the balls closer to the center of my mass, and notice how faster I'm spinning. And when I bring them out, I slow down. And as you can see, this is exactly what happens to the interstellar cloud.
The large molecular cloud had a small rotation. When it shrank, this rotation speeded up.
This rotation was caused by the Big Bang.
Contracted.
Remember, we're moving.
The energy of the material flying in from space caused its center to heat up. This spinning ball became our sun. The rest of the cloud was spinning so fast that it spread out into a vast disk of dust and gas.
Those would be important.
This was the cradle of life.
All right, we're going to leave it at that right there. Okay, let's go back to what we were talking about. Oops, sorry. Gotta have my little corner piece over here. And then, hey, here I am. All right, so formation of the solar system. These gas clouds, again, they condensed on themselves. Why? Why do they condense on themselves? Well, they had angular momentum. Think of it like a figure skater. When a figure skater's arms and legs are out wide, they spin slowly. But as soon as they bring their legs in tighter, notice our figure skater here, let's see how much faster she spins. That's just physics, okay? The tighter the mass is towards the center, the closer to the center of gravity, then the faster you'll spin. So as this gas cloud began to spin at such a ridiculous speed that it created heat, there was friction and heat was created, and then this is what eventually formed our sun and forms almost all the stars in the universe, okay? So this occurred about 5 billion years ago. Now, around this same time that the sun was forming, remember it said that there was like gas and debris and little rocks that were forming around the sun's and those like ring-like things. Well, in those rings, these like pieces of rock and debris would smash against each other. And we're not just talking about like hitting and bouncing off. We're talking about like hitting at millions of miles an hour. They would hit with so much force that they would actually fuse together. They would melt and fuse together. So tiny little pieces of dust would hit, fuse, more pieces of dust hit, fuse, and each one that got added made it become a little bit bigger, and a little bit bigger, and a little bit bigger. This eventually is how planets would be formed. Again, we're talking about millions of years. It's not like this just happened over a week's time, okay? Over the course of a million years or so, you could get to the size, that big enough that you could start pulling other pieces of debris and rock in because you start to have gravity as your mass grows. So this would have been what the early Earth would have looked like. It would have been molten rock all the time, being just bombarded by asteroids constantly, and each time it got hit, it got just a little bit bigger. It added to its mass. Okay. Now the original solar system had 20 planets in it. Okay. Now picture that, 20 planets. We only have 8 now. We know Pluto's out there. We count that number 9. So where'd the other 11 go? And it's funny you should ask that. Okay. The formation of the Earth. Now we know the Earth formed about 4.6 billion years ago, and it formed after one of these collisions that we just got done learning about. Okay. But it wasn't just any collision. We're talking about a pretty massive collision. Oh, I knew I was going to get a flippin' advertisement. Oh, I'm sorry. Hang on, let me go back to myself here. Okay, so this collision, again, this wasn't just any collision. This collision was actually between 2 planets, between Earth and another planet called Theia. And what happened was that they would rotate around the sun, and every time they got a little bit close to each other, remember, planets have gravity because they have so much mass. And so when these 2 planets would come close to each other in their spins, they would start to move towards each other and a little bit closer and a little bit closer. And over the course of a couple of 100 million years, they got a little too close. So here you can see those rocks smashing into each other like we talked about, and you notice they're getting a little bit bigger each time that happens, and so they start to form the planets. And you can see here's our 20 planets around the sun. Each one, again, molten rock, gases, all kinds of stuff happening inside them. Okay, and again, being bombarded constantly, daily, with more and more asteroids. This is what it would have looked like just below, the surface, and it would have been a real small crust, real tiny. Like you can see how thin the crust would have been. There would have been constant reformations and cracking in the surface of the Earth. But then we get to that collision that we talked about. Okay, so we've got the Earth here, we've got Theia here. What do you suppose is about to happen? And again, this wasn't just any little like brush by. This was massive, and the whole thing probably took anywhere from 15 minutes to an hour to kind of go through the whole like collision process. But what happened was Theia again gets smashed, and parts of her and parts of the Earth go scattered around. Okay, the newly formed planet that we call Earth now. And you can see what it would have looked like. Well, just like before, those rocks and debris would start to collect upon themselves, and that actually became our moon. And as the Earth reformed, the center of Theia, which was a solid core chunk of metal, actually now became the center of our new planet. And that's why the Earth has two separate cores. It has a solid metal iron core, and then it also has a liquid core around that. It's pretty crazy, right? So, all right, so this is how, again, the Earth got to its final size. This is why we have a moon now. It's because of the Earth and Theia crashing into one another. Pretty amazing. This also caused the Earth to tilt on its axis. This is the reason we are at a 23-degree angle all the time. So without Theia, we wouldn't have our 4 seasons. Thank you, Theia. I love the fall. Okay. So as the Earth began as a ball of molten rock, again, they emitted gases because they're melting and fusing together and stuff here on our planet. And some of the gases that got emitted and became our really primitive, really thin atmosphere were methane, ammonia, hydrogen gas, and water vapor. Okay, and over 1 billion years or so, the Earth cooled enough that we got that rocky surface, and there wasn't a ton of liquid magma on the surface. And actually, what happened is, as it cooled, some of the water vapor that was in that early atmosphere fell as rain. Okay, now because it had a rocky crust, again, that rain would start to pool on the Earth's surface and became a giant ball of water, basically, with a really thin atmosphere around it. But if you think about the stuff that's in that atmosphere, we had hydrogen, nitrogen, carbon, and oxygen. Again, they were all separate as a part of different compounds. Methane has CH4, and ammonia's NH3, and hydrogen gas is H2, water vapor H2O, obviously. But it's possible that during this time, because of the heating and cooling, there could have been these gigantic thunderstorms that covered the whole planet with massive amounts of lightning and very violent thunderstorms. But because of this lightning, we actually now have the ability to do something with our gases. We can make them fuse in a certain way that you could actually become organic material from inorganic gases. And we'll talk about that more in our next segment when we talk about origins of life on our planet. But hopefully you got some pretty good information. I know you're going to have tons of questions, but please keep watching YouTube videos. There's tons of information out there about the origins of our universe, the origins of our planet. But if you have questions, feel free to contact me, at mrkubuske.wordpress.com. My email is jkubuske@gocathedral.com, or follow me on Twitter @Coach Kubuske. But I look forward to hearing from you. Please keep finding your own answers and keep formulating your own opinions. Think critically about where we come from and ask lots of questions. That's the best part about this unit, is you get to ask these amazing questions that until now have been just completely unknown to you. I'm sure a lot of you up to this point never knew that the moon came from the collision of 2 planets. I know when I first learned about it, I was like, mind blow moment. Okay, but again, feel free to contact me if you have questions. Hopefully you learned something. Otherwise, I'll see you next time when we talk about origins.